let me look at it.
I was going to say he probably does not want you not just here.
And I'm not going to be the one who steps through this.
And then I'll look at 3 other people who do the same exact same thing. So that she can. And that way it's like,
Self-updating.
so I'll,
How long have you been saying that?
Visits like 4 or 5 times right now.
Oh, I didn't see you for his dinner.
Oh, okay.
Oh, yeah, so I've done that. What about you?
That, and then I did a couple of funny books.
Oh, yeah. So I read the case that she gave us, and then the Quizlet, I compared it. The Quizlet was exactly the same.
Oh yeah, it was the same material. It's just that her questions are like exactly the same format as the one for the book. So it's helpful.
Oh, I didn't get any questions from the book. I just looked at
Oh, just the information.
the information.
Yeah.
So we're going to talk about for the next little bit neoplasia, and this is something we're going to continue on learning about throughout the year. But this is sort of a general course, or general description of neoplasia. The objectives here, there are quite a few objectives. We're going to talk about malignancy, what causes it, how these cells become malignant, looking at different things like proto-oncogenes, suppressor genes, things like P53, which is a very important gene that we all have, and so on. You guys know about these things? I mean, have you been talked to about things like P53? So maybe, okay, so we'll just kind of go over things here. The overall underlying molecular basis of cancer is this. It's damage to the chromosomes, to the gene structure from the environment. And from the environment can be chemical, radiation, viruses, and so on, or inherited, or just plain a mutation occurs out of sheer bad luck for you. Nonetheless, when a mutation occurs, and that is the bottom line of cancer, is a mutation of usually more than one gene. It has to be a non-lethal mutation. Otherwise, the cell itself won't survive. So that's important, non-lethal mutation. You get a tumor by a mutation or mutations occurring in a single cell. That single cell produces monoclonal copies of itself, but as it continues to grow and over time, there usually will be other mutations that occur. So that by the time you get a visible tumor, it's polyclonal. It says here, it's very heterogeneous, but polyclonal is probably a more accurate description. Now, how you get tumor cells, or what the genetic mutations occur that produce tumor cells, are usually a mixture of those 4 things there. Either you have activation of proto-oncogenes, and I'll talk about that in just a second, or you have suppression or inhibition of naturally occurring tumor suppressor genes. Apoptosis we know as programmed cell death. If that is evaded, then cells will grow. And finally, your cells, all of your cells, have normal DNA repair mechanisms within them. If you alter the ability to repair DNA, you increase your chances of abnormal growth. So it says carcinogenesis is a multi-step process involving multiple mutations, and that's indeed correct. Now, if you look at cellular cells themselves. What are the fundamental things that make malignant cells malignant? One is, all cells of the body respond to growth signals, or the absence of growth signals. So if you need to increase the lining of, you need to turn over the lining of your gut every day, every 24 hours, that's a programmed response to cell signals. In tumors, these cells do not have to rely on extra cellular signals for growth. They can operate with their own internal mechanisms for growth. The second thing is insensitivity to growth inhibitory signal. If you take normal cells and you plate them on, you grow them on a plate, they will grow and form a monolayer. And when they contact each other, the contact itself initiates an inhibitory signal so that they don't grow over top of each other. All cells of the body have that type of contact inhibition. Well, this is one that's lost with tumor cells. They don't stop growing and they don't recognize their neighbors. Evasion of apoptosis, I've already mentioned that. Limitless replicative potential. If you take a cell, a normal cell, and put it in a dish and grow it, it will divide a certain number of times, and then that cell culture will die. If you have normal tissue, it will die. There will only be so many daughter cells produced before the whole thing dies. That is lost with malignancy. Programmed cell death. No. Okay. If you have a tumor, in order to get the tumor to grow, it has to have a blood supply. So there has to be a signal coming from the tumor to blood vessels in the area to grow into the tumor to sustain it. And that's what that means, right? Sustained angiogenesis. If you don't, then the core of the tumor is going to die. And indeed, that's what happens in some tumors. The core becomes necrotic. Ability to invade and metastasize, defects in these, and finally, evasion of immune detection. If the mutation involves an alteration in a cell surface receptor, then you now are able to recognize it as non-self and can attack it. If the cell surface markers are the same as you, that's how tumors evade the immune system. And the issue is, when you have a visible tumor, you're usually dealing with all of these things. Now, a couple of definitions here. One of them is, let's start with the bottom one, proto-oncogene. Proto-oncogenes, these are genes that you have in your DNA. There are dozens and dozens of them. They're normal in you, and they're necessary for cellular survival. These genes, if you look right here, it says, in essence, proto-oncogenes are normal genes. The purpose of these genes is that they are involved in signal transduction, mitosis, reproduction. But they are regulated, their expression is tightly regulated. That's why your gut lining replaces itself every 24 hours. The proto-oncogenes allow the replication at that speed. However, if there is a mutation in a proto-oncogene that releases that protein to be transcribed and translated at an increased rate or without any checks and balances, it now becomes an oncogene, and you wind up with cells that replicate abnormally. That's the bottom line. So if you read these two paragraphs, that explains what I just said. Proto-oncogenes are normal. When they are activated by a mutation in the gene that codes for that protein, they become an oncogene. Here's a whole list of oncogenes here. Understand that these have been activated. And there are a whole bunch of them here. We've got the RAS genes, SARC, MIC, FOS, and so on. This is what happens when they're activated. They, through mutation in the genetic material itself, or the gene is amplified. There's a chromosome defect that causes the gene to amplify to produce more of the protein, and so on. This is what happens in terms of the function of that protein. The normal function of the proto-oncogene is this, but when they're activated, this becomes abnormal. So if you've got a transcription factor that's normally produced at 1 a day, now it's 100 a day. On top of that, you've got a cell cycle regulator that normally it's once a day, now it's 1,000 times a day, and so on. And those things produce these types of tumors. Now, I don't want you to go learn this table here. I want you to understand the mechanism. That's the important one. But if you look at this, if you look at these things right here and take it to the next slide, here's our big cell here. There's gene regulation right there. Look at where these things are. RAS, we've got FOS, FOS is right there. SARC is there. You can find these regulatory proteins. Now this lists the gene, but understand, behind each gene is a protein that regulates cell proliferation by that mechanism. Now if you look over here, we've got gene regulation, cell proliferation. They go hand in hand, and this is a tightly regulated bunch. I want you to look over here at the bottom left here, because we're going to pick it up later on. Apoptosis, where you've got a BAX and you've got P53. Those are related to apoptosis. So we're going to hang on to those right there. Later on, we'll pick them up. Okay? All right. Oh no. The reason I said, oh no, is because I redid this. You see how the thing is curved? Is yours curved?
Yeah.
Oh man, I made them all flat. Oh, well, I'll resend that to you. Because this is ugly. I got to think, I stayed up all freaking night. I cut out these things out of the book in order to make them flat for you. And this is the old one. Dang. All right. Well, the purpose of this slide is this. If we take something like melanoma that I've highlighted, I have arrows pointing to, we can see that when you're talking about something like melanoma, there are different processes that can lead to melanoma. And in fact, it's not just one of these, it's not an issue with a cell cycle regulator. When you have a melanoma, you have some of those cells with this mutation, some of the cells with signal transduction, and so on. So that's why you get different tumors that show up in multiple places on this slide, because there are multiple types of genes or oncogenes that can lead to those tumors. Now, one of them that's, it's not a point mutation, it's not an inheritance issue, it's a translocation of genes. And here are a couple of examples here. We have two of them. One of them is Burkitt's lymphoma, and the other one is CML, chronic myelogenous leukemia. These disorders are due to translocation of pieces of chromosome, but unfortunately, the translocation activates the proto-oncogene into an oncogene. In the case of CML, one of the things you look for in the chromosome study is this little booger right here, where that piece of the chromosome has now translocated to this chromosome. That's called the Philadelphia chromosome. The presence of a Philadelphia chromosome in CML portends a better outcome. If you have CML without the Philadelphia chromosome, the prognosis is worse. The prognosis is not good anyway, but it's even worse without the Philadelphia chromosome. So the board question, Philadelphia chromosome equals CML, and you'll learn later on that CML is a disease of people my age. So it's a really bad type of leukemia. Now there are several, Burkitt's lymphoma is another one, Burkitt's lymphoma. ALL, acute lymphocytic leukemia, is the #1 malignancy of childhood. And it too is a translocation type of issue. In this slide right here, it says representative tumor suppressor genes. So now we're going to switch gears. We dealt with oncogenes. We dealt with inheritance, translocation. Now let's switch to suppressor genes. You have quite a few genes in your DNA whose sole task is to regulate cell reproduction. Okay? You see a whole bunch of them are listed here. P53 is one of them we've already talked about. Brca. You understand that you have Brca, or Brca, however you want to say it. You have it. You normally have it. Males and females. It's a mutation of Brca that's the problem. It's a mutation of all of these, the neurofibromatosis tumor suppressor gene, and so on. The retinoblastoma gene. And these are suppressor genes. How they act is, let's see, I'm going to say, mechanism, no, that's the mechanism of inaction. They're not specifically telling you whether or not it's a cell cycle regulator or so on. But if you look over here to the far right, the inherited syndromes that are the outcomes of these inactivation of suppressor genes, pretty impressive. Neurofibromatosis, von Recklinghausen's disease. Familial adenomatous polyposis is another one. Retinoblastoma of childhood, really. Okay. The top one there, Lee Framini disease. is associated with P53. And I'll speak of it in just a minute. If we look at what these things look like, this is retinoblastoma, and we'll go over the development of it later on. But the bottom line is, during the physical exam of a child, an infant, you want to also always check for the presence of the red reflex. You know, if you take your ophthalmoscope and if I just turned off the light and shined it at you, I can see your red reflex. You all look like a bunch of cats. You know, it's very impressive. In retinoblastoma, the absence of that red reflex is a huge red flag. And that's why you always check the red reflex during well child checks. This is familial adenomatous polyposis here, where you look at the colon and it's just covered with thousands of polyps. These things are so prone to malignancy that the treatment for this is total colectomy as a teenager. Because by the time you're in your 20s, there is a 100% chance that you will develop colon cancer. That's why if you wind up with this disorder, you won't wind up with it now, but if you have a patient with this disorder, the only treatment for it is total colectomy in the teenage years. Can you imagine what it's like to tell a teenager they're going to lose their entire colon? So,
How would that present in the office?
most of the time bleeding, rectal bleeding, dark stools. So this is a Wilms tumor up at the top here. This is a common tumor of children. This is why you do it, you feel for the kidneys when you do an abdominal exam on a child. Very common tumor. The bottom is is von Recklinghausen's disease, neurofibromatosis, where you have these tumors. They're benign tumors, but they occur along the nerves of the body. And for the most part, it's just a cosmetic issue, but it can be a disfiguring issue if these things get really large, or if they occur on the optic nerve or the vestibulocochlear nerve, something like that. They can produce obvious defects. I've seen this many times in my career. You go to Penn Square Mall, you walk around and be observant, you'll probably see somebody with it. Interesting, these things develop as you get older. They're not present in children. But one of the telltale signs that this disorder is apparent is if you see during your well child check, this is another thing you look at, you look at the skin. If you see 6 or more, they're called cafe au lait spots, they're brown pigmented spots. If you see 6 or more, that's a telltale, that's pathognomonic for, it's not absolute, but well, I guess that is counter, that statement is counter. You have a high index of suspicion for neurofibromatosis. Okay. 6 or more cafe au lait spots. All right. Let's talk about P53 for a second. So look at how important this is in terms of cancer in development. First of all, P53 is called the guardian of the genome. It looks over several hundred genes. It's a protein that itself is transcribed from a gene, right? Everybody follow me that. It's a protein. This is not a gene. All right, so P53 protein, essentially think of it as a housekeeper going from gene to gene, scrolling up the DNA, down another DNA, making sure that the DNA is what is described as not stressed. And by not stressed, I mean there are no breaks, no mismatches, that the base sequence appears correct. Also that the cell is not stressed in terms of hypoxia. Okay. And that, you guys know what telomeres are? You guys know what telomeres are? Okay. So the shorter the telomeres, the more risky the cell becomes. So it's also, if you think of it, kind of counting the telomeres in the DNA. Nonetheless, 50% of all cancers, if you look at all cancers, 50% of them have a defect here in P53. Half of all cancers have a defect in P53. That's not the only defect. In addition to P53, you're probably talking about tumor suppressor issues, you're talking about oncogenes, and so on, but half of them have P53 issues. If you look at these right here, lung, colon, and breast cancer, 100% of them have a defect in P53. There's nothing in medicine that's 100%. So that's a pretty bold statement right there. Every visible lung cancer has a defect in P53 as part of its polyclonal makeup. That's important, though. That's important. All right. Go on down here. There are a couple of other proteins that are present in the cell that bind to P53 and degrade it over time. Now, in the instance of stress that I mentioned earlier, P53 goes through a post-transcriptional modification, not a post-translational modification, a transcriptional modification of the DNA itself to release it from the binding degradation protein, and allows it to initiate the transcription of certain genes. Those genes have one of two functions. They either, right here, they either induce cell cycle arrest or they initiate apoptosis. Now, if I start out and if I've got a stressed cell here, well, there is a defect in the chromosomes here. It looks like some proto-oncogenes are now activated to oncogenes. P53 is going to shut that cell down and not allow it to replicate by interfering with the cell cycle. It will make that cell quiescent. Quiescent means it stops reproduction. If the cell is able to repair that DNA, in other words, fix that oncogene back to a proto-oncogene, then the P53 will separate and allow the cell to continue. But if the cell cannot repair it, it will initiate apoptosis, so the cell dies. That's a pretty cool mechanism. That's a pretty cool mechanism. But the problem is, so many tumors have a defect in P53. What's the purpose of chemotherapy and radiation therapy? It's to induce chromosome damage. If you have tumors with intact P53 mechanisms, then the chemotherapy and radiation therapy will probably work. P53 recognizes these as damaged chromosomes. We're going to quiescent the cell. You can't fix it, we're going to kill it. But if P53 itself is damaged, then chemotherapy and radiation therapy are not gonna work. That's this last statement right here. Testicular cancers, acute lymphocytic leukemia, they respond well to chemo and radiation. If you think about ALL, remember what the problem was with ALL, it was a translocation problem. Had nothing to do with P53. That's why 40 years ago, 50 years ago, if your child had ALL, if your 3-year-old had ALL, that child was going to be dead within 6 months. And now, it's almost curative. If you get it early enough, you can cure ALL, which is amazing. But lung cancer, colon cancer, no. If you have metastatic colon cancer or metastatic lung cancer, as I'll go over later on when we talk about tumors specifically, the 5-year survival is horrible. 5-year survival is horrible.
Why do kids have a harder time of surviving AML compared to adults? Because, I don't know, it's just weird how adults can battle it a lot easier than kids. I don't know if it's the chemo or is it something to do with the
Are you
receptor?
saying ALL versus CML?
No, AML.
Myelogenous leukemia, completely different animal, completely different animal. Next week, I think it's next week. Yeah, it is next week. I'm going to go over hematopoiesis, and we'll talk about the myelogenous cell lines versus lymphocytic cell lines, completely different animal. All right, this is the whole thing summarized here. We've got environmental issues that produce damage. If you can repair it, great, you can move on. If you can't repair it, if you're dealing with oncogenes or suppressor genes or whatnot, you're gonna wind up with proliferation, unregulated proliferation, or decreased apoptosis. It's the same thing. Well, it's not the same thing, but it's the same outcome. Clonal expansion, mutations producing different polyclonal structure, and then there you go. Okay? Any questions about that? Okay, let's look at some principles of neoplasia. Bottom line, it means new growth. Neoplasia. It's not always bad. I mean, it's never good, but it's not always a death sentence. The single cell we talked about, it starts that out, but then polyclonal by the time you get to the end. Note that neoplasia has no physiologic function. If you have a neoplasm in your liver, that tumor is not conjugating bilirubin, it's not producing bile, it's not in a normal physiologic way. You remember from anatomy, all those tumors that we were able to dissect out, they definitely don't have the same color as the surrounding tissue or the same consistency as it says in the next one there. And of course, tumors are going to have no restraints on orderly growth, and that's why cancer, and I think I mentioned this in anatomy, usually will have tendrils. Instead of, one of the hallmark characteristics of melanoma is irregular borders. If you have something with nice, well-defined borders, that's probably not a melanoma. If you find a breast mass that feels like a marble with nice, defined borders, that's probably not breast cancer. Breast cancer is diffuse. Melanoma is diffuse. Okay? Replication over differentiation. In tumors, what you're going to find are a lot of mitotic cells in different stages of mitosis. Normally in the skin, you're going to see, if you're looking at a centimeter of skin, you might look at 3 or 4, you might find 3 or 4 keratinocytes that are undergoing mitosis. But in a tumor, There are going to be hundreds, and they're going to be in different stages. Differentiation is another thing. If you have a tumor, so when I talk about hematopoiesis on Monday, I think it's Monday, I'm going to tell you that like if you're talking about a white blood cell, this would be the stem cell. This is the stem cell, and then you're going to have blastic type phases of maturation, and then they're going to be a little bit more mature, and they're going to turn to cytic, or something myelocyte versus myeloblast. So there are different stages of maturation. That's what that means there about differentiation. If you have a malignancy, if that malignant cell arises from this myeloblast, it is more lethal than if it arose from a myelocyte. The more highly differentiated the cell is, the less likely it's going to divide at a very high rate. Matter of fact, in CML and CLL, chronic lymphocytic leukemia, what happens is you can treat these people and they're going along just fine, and all of a sudden they have what's called a blast crisis. And you wind up with their blood, instead of having maybe a couple of hundred blast cells in it, becomes inundated with blast cells, and that's how you die. Blast crisis is usually what will kill somebody with CML or CLL. Chronic leukemias, not the acute leukemias. All right. Replicate the absence of normal signals. We've talked about that. Some neoplasias have definite genetic origin. I mentioned that, and I'll show you again, like the familial polyposis. But most are due to the cumulative effects of environmental factors. Now, you have certain mechanisms that work against cancer that are really good. One of them is you have this huge P53 and chromosome repair mechanisms in all of your cells, normally. You have things like apoptosis and senescence. I mentioned quiescence. P53 induces quiescence, a pause. Senescence is the eventual death of that cell. So there's a difference between quiescence and senescence. Quiescence, the cell can bounce back. Senescence is the cell's going to sit there until it dies. We talked about blood vessels. And then you always got to appreciate physiologic or anatomic barriers like the basement membrane of your skin. As long as that melanoma is superficial to the basement membrane, you will not die of melanoma. But once it gets below it, now there's a problem. And of course your immune system. If you look at, this is about 10 years old, so if you look at the incidence of cancer in males and females, and in cancer deaths, there's a little bit of a difference there between the two. But if you let's just focus on death here. In males, and this hasn't changed since then, most of the deaths due to cancer in males are due to lung. For many, many years, the deaths in females of cancer, it was due to breast. But then beginning in about the early 2000s, the lung caught up and surpassed breast as the #1 cancer killer in women, and this is how it still is. Okay, we were doing great things in terms of declining cancer death rates, or the death due to cancer, until hepatitis C human papillomavirus, and drugs got so popular. Hepatitis C, we're talking about hepatocellular carcinoma, adenocarcinoma. For HPV, we're talking about squamous cell carcinoma, the mouth, the anus, and cervical cancer. In HIV, you're looking at things like Kaposi sarcoma, and then everything else associated with it. But overall, 1 in 5 folks will get cancer in their lifetime. That's the lifetime risk of developing cancer, 1 in 5. All right, now here's a phenomenon that's kind of interesting. If you take folks in Japan and look at these different types of cancers and compare them with people that live in California, you'll see that the distribution of these types of cancers is pretty symmetric in California, but way asymmetric in Japan. We have a problem with colon cancer over here. Japan has a much lower incidence of colon cancer, but they have a huge incidence related to Americans in stomach cancer. Stomach cancer is not a good cancer to get. However, if you move from Japan to California, the incidence of these things start coming down. And then if you start looking at kids from those, it comes down further. And eventually, over time, it will be the same, indicating that there is definitely an environmental component to the development of malignancy. And by the way, all of those cancers are malignancies. What determines what is a malignancy? Well, let's do a little nomenclature here. You hear benign and malignant all the time. It's basically an observation of the cell type. When they do a biopsy, if you have breast cancer, cancer is a neoplasm, right? Cancer is a neoplasm. Neoplasm is new growth. If you have a lump in your breast, you have a neoplasm. That's it. That thing can be benign or malignant. How do you know? Well, you know when you biopsy it and look at it under a microscope. If that tumor resembles the normal morphology of the surrounding tissue, if it has the normal number of chromosomes, same number of mitogenic appearance, that's benign. But if it just looks like a mishmash of cell reproduction, if it has not a normal capsule or normal borders that are all over the place, then that is telling you this thing is aggressive. You can look at it and define it as aggressive. If it's benign, it's not aggressive. If it's malignant, it's aggressive. Malignant does not mean metastasis. Those are two words you have to separate. You can have a non-metastasized malignancy. And most benign tumors will not metastasize. Benign tumors are more differentiated. Malignancies are less so. If you're looking at metastasis, it's just spread to some point other than the primary site. And that spread can be through the blood, it can be through lymphatics, it can be through transcelomic seeding. Transcelomic seeding is what happens with ovarian cancer. You get the cancer that leaves the capsule of the ovary and you get seeding of new growth, neoplasia, throughout the bowel. We talked before about ascites is one of the telltale presenting symptoms of ovarian cancer. That's why. You have an intraperitoneum that's full of malignancy. Another term you need to know is carcinoma in situ. Carcinoma means of the epithelium. In situ means in place. So if the carcinoma is there, and it's just there, that's what you call it, a CIS, carcinoma in situ. If it penetrates the capsule or the basement membrane or whatever anatomic barrier, then it's no longer in situ. Carcinoma in situ essentially just means it's confined. When you're talking about the cervix, one of the designations that you'll get back on a PAP report is an SIL. That means squamous intraepithelial lesion. Squamous intraepithelial lesion. In other words, there's those cells, those squamous cells there do not have the normal appearance of cervical epithelium. But they're there on the surface, they're not penetrating through the basement membrane. It's SIL. Ductal carcinoma is a breast cancer that's confined to the duct itself. It hasn't penetrated the basement membrane. If left alone, which is what it's getting ready to say here, I don't think I finished that clause. If left alone, though, carcinoma in situ will develop into malignancy. Or metastasis, I should say. Not malignancy, metastasis. Now, there's a TNM staging system for tumors, and that's what this means right here. And I'll go over it, I think, the very last slide. If you do a biopsy and you get the report back TISNOMO, that means that there's no nodal involvement and no metastasis. You have a tumor in situ. Hyperplasia and hypertrophy, I think we've been over, in dysplasia, we've been over these terms before. The one that I don't think we've been over is anaplasia. And anaplasia is a dedifferentiated cell. You should never have blast cells in your circulation. In leukemia, you do. Dysplasia, terms like poikilocytosis means that it's irregular shaped, essentially. Not irregular shape. Irregular appearance. That's not exactly the right word either. Yeah, it is. We'll say irregular appearance. Anisocytosis means they're irregularly shaped. Hyperchromatism means that when you stain these cells, the nucleus or nucleolus is going to be intensely blue. Let's just say that. Hematoxylin and eosin. You know these stains, right? H&E stains. The bottom line is, when you're on Jeopardy, is blue is bad. Blue is bad. A physician friend of mine, she said, the only thing I remember from an entire year of pathology in medical school is that blue is bad. All right. Metaplasia we talked about in terms of the esophagus and barracks. Here's a nice little cartoon showing the difference between hyperplasia and invasive carcinoma. This is another nice little cartoon showing a transformed cell at the top. I think that's what that cell says. Developing into the primary tumor. And then the primary tumor making its way through the basement membrane into the connective tissue, going intravascularly. Once it's into intravascular, these things can seed themselves in various places throughout the body, depending on the anatomy. Most of the places they're going to seed are going to be where you would wind up with a ball of these things getting stuck, will be in a tissue that's capillary or sinusoidal in nature. Like if you have, I'll say it again, the places where these tumor balls get stuck will be in anatomical locations that are capillary based or sinusoidal based. A sinusoid would be like, think of the marrow of your bone. You've got this big, fluid-filled thing with these spicules and stuff all in there. It's not a nice vessel going through there. It's just a big, open thing. Your spleen is the same way. Blood just dumps into your sinusoids of the spleen and interacts with splenic cells and recollects into the splenic veins, but it's a big sinusoid. Your vertebra, the bodies are sinusoidal. Capillaries, where things get stuck, would be in your lungs. Think of pulmonary emboli, they get stuck. It's the same, it'd be an embolus of tumor cells. The liver is another place. The liver is a huge capillary network for filtration, detoxification, and all that stuff. The brain is another place where you can wind up with seeding through capillaries. Interesting thing about the brain, primary tumors of the brain rarely leave the brain because they don't get through the blood-brain barrier coming the other way. But tumors from other sites can penetrate the blood-brain barrier going from vascular to brain. You're never going to see a glioblastoma in the liver. Okay. Why don't you take a break and then we'll come back.
Holy crap. I got some orthostatic hydration for a second. I got it going.
Little cafe. Did he really love it?
Me too. So I have to really I sit under it like all day and I'm just like, that's weird.
How hot did you put your heat up?
I think it was night. It was during but during the day, I could get up to 8.
So she's like ripping off the thing, and then there's people who are like, that's horrible. Like, I think it was like a real deal. Oh, I haven't. I haven't put her own. I should have brought it.
Should have.
You definitely need to get yeah, my head started to hurt because I can't breathe. I hate breathing out of my mouth.
Do you want some?
Breathe out of my mouth.
I do, because I can never breathe through my nose.
My hand off. Maybe about to pass out.
It was good. Where did you find that?
Yeah.
can't even watch.
Right.
And they did a liver biopsy to see if they could start That's my list of things I don't know. That's what must have
It was a graze, okay. It was a graze.
I never knew that.
No, I don't know. I just am making things up because that's literally what I heard is that people were given and like that's why he didn't survive very long is because his heart just kind of collapsed. I don't know if that's
So you were
yeah, I was in my closet this morning and I was like, what can I wear today? And I saw my leggings and I like literally just started like jumping in place like, yes, I get to wear that today.
I got a text from my eye doctor saying it was time to come in and I was like, sure, my timing. Yeah, I'm going to.
You have pockets in your pants.
Yeah. Well,
I know.
don't come like that.
They're like, really? They don't make them.
They really don't. It's
That is sweatpants, those are not jeans.
Yeah, that's what we're doing.
Or even dress pants. Even dress pants don't.
Yeah, dress pants are very good. Although a lot of times they're so shut, we have to cut them open. Yeah, but even then they're really small.
Right. Like enough for your chest.
Yeah, my pants yesterday did not have mine are like they're sewn in, but like they're so small. I'm like, I'm sewing them. Yeah, there's some that I'm like, they're like this big. I'm like, why did you even? Why'd you bother? Yeah.
I think it originally started as like a power thing. Like if women couldn't carry their stuff, then someone else had to carry it for them. I think I read that. And like apparently that's still an issue. Why can't we have pockets?
Yeah, but now we're all independent and carry it ourselves, and I want pockets right now.
Right.
now you're just would you just if you had large pockets, would you carry
Not as often. I would still sometimes.
Well, I don't wear them. Lately for this, I carry a wallet that holds my money in it. I never carry that. Yeah, I try to. I gotta say someone else one of my partners that has the same face. I try to win where I have at least one pocket. We were with. I wore an extra jacket just so I wouldn't have to like dig in my bag for it.
I don't even try because I don't.